Hi, I'm Kieren.
And I'm Riku.
And welcome to Artificially Ever After. For today's episode,
AlphaFold, AI's biggest breakthrough.
Okay. Hi, everyone.
Thanks for tuning in.
Yeah, welcome back.
So today we're going to talk about AlphaFold, and as the title suggests, it is a pretty big deal in terms of what AI is capable of achieving.
It is. And another bio episode. We've got another one for you that's part of this AIBIO-UK series. Yeah, we're going to be weaving in some non-bio episodes after this one for those of you out there who maybe biology isn't your cup of tea, but hopefully we can convey the fact that this actually is a really interesting and important application of AI that even if you're not interested in biology, probably, if it hasn't already, at some point in the future, will actually impact you and affect your life somehow.
Yeah, and even if biology might not be a cup of tea, as a living, breathing organism, you should be interested because AlphaFold is all about understanding how proteins fold, and proteins are basically the building blocks of all life. So we actually see them in all living organisms, and how they fold and their structure is core to their functionality.
Yeah.
And just to build on this a bit more, so protein functions govern how your tissues are built and repaired. So if you go to the gym, then it's very important. They catalyze a lot of your chemical reactions. So I don't know if any of you can't have an ice cream because of your lactose intolerance, but sadly to say that is just because of the proteins.
My heart does go out for those people.
Yeah, and cheese, right?
Yeah,
And also proteins are also the roots to certain neurological diseases such as Alzheimer's. So you can imagine that if an AI model can predict these structures really well, that could be really useful.
Yeah, and they're involved in kind of cellular structure or cellular functions all through the different scales of life as well. Communication from chemicals in your body and hormones, and they can defend the body as antibodies. So basically, everything that's going in your body, everything that's going on in all living organisms, there's some link to proteins there. So they're just so important. And, it's because of this versatility that they're so important. And they're able to undertake so many different functions across, so many different organisms, so many different scales of life, as we just said. And this is all tied to their structure, as this 3D shape determines what they do, and this variety of things that they can do. So, they also have so much more scope and variety than other biomolecules. So they're by far the most varied. And understanding this structure and how they fold is crucial to understanding what type of functionality they will have and what they're doing within a certain organism.
So clearly understanding how proteins work is super important. And we're now in a really exciting age in AI, at least, where this model called AlphaFold that was developed by Google DeepMind and Isomorphic Labs uses AI to understand proteins, and it's been doing really well.
Yeah.
So much so that it's been said to usher a whole new era for biology and chemistry as a whole. And the Forbes magazine actually said that it's the most important achievement in AI ever.
Yes.
And obviously that's in this world of large language models that everyone seems to be talking about. So
exactly, yeah.
Yeah, and the developers actually got a Nobel Prize just last year. So hopefully that speaks volumes to just how incredible this AlphaFold thing really is.
Yeah, but to help us with our discussion today and conveying this incredible AI innovation, AlphaFold, we have a very special guest who is going to be coming on later in the episode, who is Dr. Jennifer Fleming. And she is the coordinator of the Protein Data Bank in Europe, the PDBe, which is this enormous online database of all these proteins, their structures, and all this information about them, as well as this database of AlphaFold's predictions of the structures of these proteins, the AlphaFold Protein Structure Database. So she's the coordinator and overseer of all of this, and she's going to be coming on to help us to understand how AlphaFold as a tool and its insights are being shared within the broader scientific community, and how that's then helping to facilitate so much discovery and innovation that's going on in the field at the moment, and all this exciting rapid development that we've been seeing over the past few years since it's come out. So yeah, very exciting and honoured to have Jennifer on, and yeah, she'll be coming on kind of more in the second half when we start talking about the impacts of AlphaFold.
Yeah, I feel really, really lucky to have Jennifer on. So should we talk a bit about the episode plan?
Let's do it.
Cool. So in the first segment, we'll do classic Artificially Ever After style, where we go look at the historical challenge and get an appreciation of the journey that led up to AlphaFold and exactly what the problem it was that it solved. And then we're going to do a big, hefty bit of demystifying on how AlphaFold actually works. So I think that it is really exciting and fairly intuitive, hopefully.
Yeah, and also kind of relevant in the world we are living in today with chatbots, right? Because there are some kind of parallels and analogies that we can draw between the two since AlphaFold's come out.
Yes, exactly. And then we'll do our fun facts after that. Following this, we'll talk about the ethics and a bit more about the data set itself. So the idea is in the first half, we'll understand what's going on. And then in the second half, we can apply that knowledge to a bit more of the ethical sides of it, the accessibility. And then we'll look forwards, see whether we're looking towards a brighter future or not.
And obviously we've said just in that intro then how impactful it is. We're going to look forward as to the breakthroughs which it's been facilitating and hopefully what it might help us to achieve in the future.
Yeah, so hopefully this message conveys that there are other amazing AI tools and they aren't just chatbots in this world.
Yes.
So,
non-chatbot AIs.
Yeah.
We've not spoken about them enough recently.
That is so true.
Okay, let's get into it.
Let's do it.
Okay, so we were slightly beating around the bush in that intro a little bit around what AlphaFold's exactly doing, what this kind of quote-unquote problem is that it also quote-unquote solved. But just to give a tiny bit of background, some, a bit of bio knowledge before we get into it. So just looking at proteins, I've obviously described how important they are across all different organisms. They have so many different functions, described as these sort of molecular machines, the machinery within cells, above a cellular level, all the way through our bodies and different living organisms as well. And they are made up of a sequence of what are known as amino acids. So these are the kind of smaller building blocks which then go on to make up the larger molecules, which are proteins. And there are 20 different types of amino acids. And proteins themselves can be made from just a few dozen of these little building blocks. So, a fairly small number of amino acids all the way to kind of several thousands of them. So that, again, there's part of the variation and kind of variety that you can have in proteins as well. It's just how many amino acids they're made up of. But then the important part is that these kind of chains of amino acids, they don't just stay in 1D. So they then fold into a complex 3D structure, which if you've ever seen a photo of it, kind of just looks like a big messy ball. It's not like some very organized kind of angular structure. It's just a bit of a globular mess, which gives you a bit of intuition as to how hard the problem is. It's not as if it's this line that's going into a nice square or something. But yes, they fold into this complex 3D structure, which then dictates their function and what they do within an organism. Again, just to give you some intuition as to why this structure is important. So the 3D shape of the protein and an amino acid sequence dictates how it can bind and link with other structures and molecules within organisms. So think of like a key fitting into a lock. So, it can only bind to certain things and catalyze certain reactions and have certain functions given the right shape that fits into the right sort of slot. So that's one reason. We also see that the structure gives different proteins and then the kind of subsequent compounds different mechanical properties as well. So one of the really cool things which AlphaFold helps uncover, which we're going to talk about later, is a kind of certain motor protein. So you can Google this online, and it literally has this amazing dynamic structure in the protein that helps it to move within 3D space. So it's it's almost like it has an actual motor on it, which allows it to kind of propel through fluids. And again, this is obviously dictated by how the amino acid sequences fold, and then they form this amazing, very intricate and elegantly designed 3D shape, which has a particular function. And lastly, they can be optimized for different environments as well. So that 3D structure can determine whether the molecule is hydrophobic or kind of water repelling. And then you can also have certain aspects of a molecule which absorb fluids and have different material properties. So all of this is linked to that 3D structure that these amino acids sequences form into. And that therefore means that if we have an amino acid sequence that misfolds, so, for whatever reason, in that really complex process of it going from that string of amino acids into this 3D globule, it a small section goes into the wrong place or it misfolds, in a slightly different direction, this can have consequences within an organism as well. So we can have it lose its function. If it's really specific how this protein folds, that it does a certain thing, if it misfolds, it's kind of intuitive to understand that it can no longer do that function anymore. But we can also have the opposite, where if it folds in an incorrect way, it can have a toxic or dangerous gain of function. So a really quick example of that is in certain neurodegenerative diseases like Alzheimer's and Parkinson's. So if we have these proteins that misfold, it allows them to aggregate into plaques, which I think we now know from the latest research largely leads to the negative consequences in the brain from these plaque formations, which is due to kind of misfolding partly. So, understanding what happens if a protein misfolds can also help us to predict and understand all of these negative outcomes and diseases which might occur. So that's why the structure is really important, and why we want to understand how we go from this sequence and this chain of these building blocks, these amino acids, to its 3D structure. This motivates why we want to do that. This grand challenge is basically to see if we can predict what that 3D structure will be just from looking at what those sequences of amino acids are. So from, if we look at the chain just in 1D, we have those, we have a line of those amino acids on our computer or something. Can we have a model, a machine learning tool that can predict how it will fold and what that 3D structure will look like, and therefore what function it will have, or what a kind of mutation will cause if it's a misfold? And the reason and the motivation for this is largely because it's a lot quicker and cheaper to understand the sequence of those amino acids and to take a protein and to sequence it and look at what all those building blocks are than to really painstakingly understand its 3D structure, because it's a much more complex and time-consuming experimental process involving what's called X-ray crystallography to detect and to determine that 3D structure experimentally.
Wow. So what I'm getting from that is the structure is incredibly important for so many different pieces of biology, but it's also so complicated. And I guess you could think of it as, if you have a protein, you can have a house and you could just knock it down and you can figure out what it was made of. But it's quite hard to just look at a house and know exactly how it's structured. Is that a good analogy? I'm just trying to understand why the sequencing task is easier than...
Yeah, it's a really nice analogy, and I think extending it slightly is basically the experimental procedure to determine the structure of the house without knocking it down is really difficult. So
right,
yeah, you're correct. It's easier to just knock it down. And if we could go from the bricks to then look at what the house was before we knocked it down, that would be great.
Cool. Okay, nice. The other key takeaway is just how difficult it is to actually determine the structure. And one of the ways to do this is called X-ray crystallography. And even though it can be done, it does take an incredibly long time. So in 1962, the first protein structure was figured out, but it took 12 years just to create this first structure. So you can imagine just how expensive it is just to determine the structure of one protein if this is the only method you've got.
Yeah, and another fun fact too, with that first ever protein structure, which is of myoglobin, which is like hemoglobin, but it's storing oxygen in your muscles. But you also need a lot of the protein from the technique as well. So in order to do that X-ray crystallography, especially back then in the early days, so they actually got loads of the protein from a whale. Oh, wow. So that they had enough myoglobin, because whales have loads and loads of myoglobin because they dive really deep under the ocean and they need to store lots of oxygen. And yeah, that was how they had to get enough of it to determine the 3D structure of myoglobin. So yes, very, very slow and long and expensive task. But we're now going to bring in Jennifer Fleming quickly, because you don't have to just take our word for all of this, because Jennifer, throughout her career, has spent a lot of time in the lab actually solving protein structures and knows firsthand how painstaking it is and why it's such a slow and expensive process. So here she is to shed some light on that.
Okay, so it costs so much because you have to basically make the protein within another organism, usually either the very first structures that were created, where they would have to get enough of this protein together in order to do the further down experiments. And they used to get it from like whale muscle, was how they originally did it. So the first structures that you have are things that are taken from where you could get a lot of material and you extract from the natural source. Then thankfully there's advances with PCR and cloning, etc. And then you could make recombinant proteins, but it's still not always cheap and easy. Even the cheap and easy versions that people use, you have to purify it, and you have to get it to such a high degree of purity, and this causes loss and loss of material. And then you have this kind of step with, I used to be an X-ray crystallographer, and in order to be, you fire X-rays at crystals in order to see the internal structure of the crystal. So you have to somehow encourage this protein to crystallize. And there's also things that crystallize easily, like salts. They crystallize really easily, but proteins, they've got a lot of moving parts. They don't want to form into a regular structure like a crystal. And it's a bit of a almost chance. No one knows how to predict that, whether it's going to work or not. There's definitely things that make it not work, but to know whether it's going to work or not is hard. So, I mean, I had one protein structure myself that took over 7 years of trying different variants of the protein, how to purify it, make it shorter, longer, give it a friend, all this sort of thing. The quickest I ever had was 6 weeks, but they can really take a long time to get it all together. There are lots of steps and things that have to be done. So I've heard all sorts of numbers how much it costs to make this, but yeah, people's time, equipment time, and expertise and chance. So that's why it's so difficult, and it's still difficult. So there's still, people still want to do the crystal structures as well. But
well, that does say a lot. That I think Jennifer mentioned that one of the sequences took 7 years. So even since 1962, it took some time.
Yeah.
So just to put this into more mathematical and hopefully intuitive terms.
Since we're not biologists.
Yeah, well, I'm definitely not a biologist. So if you imagine a Rubik's Cube.
Okay.
There are 10 million trillion possible configurations of the cube. So you might think that's a lot, right?
Yeah.
And then let's also think about every atom in the universe. The number has 80 zeros, right?
Okay.
So if you were to give me the protein sequence, the number of possible structures of that sequence.
It's just an average length sequence.
Sure, yeah. Will have 300 zeros on it. So we're talking way more possible combinations than the number of atoms in the universe.
For how it can fold, yeah.
And yeah, if you had this crazy machine that would check every single combination, let's say you do one every trillionth of a second, it would take thousands of times of the age of the universe to do.
So we can't brute force it, is the...
Yeah, you can't just, pick all the possible combinations and check them all
out.
Yeah,
wow.
yeah.
Okay. So on that note, I think you now are convinced that it's a very hard problem. Now let's go into a little bit of the history of trying to solve this problem. So yeah, I think a few research groups and people that were aware of this protein folding problem had started to look towards computational methods to solve it in the kind of late 20th century. However, it was really from 1994 onwards that we saw a massive boom in people looking towards computers and specifically machine learning to try and solve this problem, because in 1994 was the initiation of what was known as the CASP competition, which is the Critical Assessment of Structure Predictions. There was no cash prize in this competition, but it was definitely just a kind of reputational prize if you could solve the problem. But it was basically developed to try and spur on new methods and bring new research and insight into this problem, because it was taking so long and a lot harder than maybe people were initially expecting to get computers to solve this. So just in a nutshell, the way the competition works is that every 2 years you'd have all these researchers and different lab groups come together with their computational method that they've developed, and they would be given a set of amino acid sequences, and they had to use their respective method to try and predict what that 3D structure would be. And these would be new protein structures that experimentalists had kind of just determined but had never released publicly, and this would be the test. So it would be how close the predictions could be to those actual experimentally determined ones without having ever seen them before. And the metric to measure how close you were was this thing called the global distance test, the GDT, and it basically goes from 0 to 100. Unsurprisingly, 100 being kind of perfectly aligned, and basically a score above 90 was considered to be roughly equivalent to the experimentally determined structure. So kind of to a level where it was useful enough that it was close enough, basically. And we pretty much saw that from sort of 2006 to 2016, so for like a decade of this competition having been gone on for a while now, no one was really achieving above 40 at this global distance test score. So, less than half of perfect alignment, so really not very useful to biologists. And the kind of leading group at the time, before AlphaFold, who we're going to talk about shortly, was by this guy, David Baker's lab at the University of Washington in the US. And they had this tool that they developed called Rosetta. So we're not going to go too in-depth into the Rosetta algorithm, but one interesting point to note was that one of the limitations was the amount of computational power that they were able to utilize to make their predictions. And one of the kind of really cool and smart ways that they looked to solve this was by running this algorithm across loads of people's personal computers and kind of tapping into their, before we had these enormous data centers that we've talked about lots in recent episodes, they utilized the compute power from across lots of personal computers. This was how they were able to scale the performance of this Rosetta algorithm. But it also led to another quite fun and significant moment in the history of protein folding, didn't it, Riku?
Yeah, I mean, what better way to get people involved in your project other than to exploit their competitive spirit? So, yes, in 2008, David Baker's lab released Fold It, and they basically gamified this protein folding problem. So it meant that any citizen in the world could now start using this kind of simulator that's based on Rosetta. So this really good model that kind of predicts very approximately how well the structure proposed is for the sequence. And you can imagine that you're at home, you have this sequence, and you're kind of using a mouse to drag and twist and reshape this protein, a bit like what Kieren was saying, where it's this horrible cotton wool mess, and you're trying to just use your mouse to minimize this score. So in this case, you want to minimize the energy score, because I think it represents like kind of how difficult it is for that structure. So you want the easiest structure, right? It's the most stable one. So what was really cool, actually, is early career biologists, so people that obviously were researchers in biology, had intuitions about how things work in that space, definitely not myself. But they actually outperformed a lot of algorithms, and that was really nice. And in fact, a really famous success was in 2011, some Fold It players actually solved the crystal structure of a key HIV-related enzyme.
Wow.
Retroviral protease.
Okay.
All right. But and that actually stumped scientists working on it for. They were working on it for over a decade, whereas people playing Fold It managed to solve it in just 3 weeks.
No way.
So that
Very
is
cool.
a huge success.
Oh, I think I had heard about this actually, and they were all credited as authors, I think, weren't they? On the paper, it just said like the Fold It players.
Oh, really?
On the publication, yeah.
That's really cool. Oh, that's cool. So they didn't actually write the paper, but they were credited.
Yeah, because they were instrumental in solving it. Wow. And also nice that they were tapping into like human brain power rather than the kind of computer algorithms, working really hard and getting really hot trying to solve it. So
I mean, this day and age, get ChatGPT.
I was going to say, maybe we could take some inspiration there with the chatbot world today.
Yeah. So the main message here is actually that this protein solving problem could kind of be solved with enough human intuition and obviously scaling up to the world. But the point is, humans were able to find patterns. So that actually led into massively Google DeepMind's approach with AlphaFold. So for those of you not aware, one of the biggest breakthroughs that DeepMind have under their belt is their AlphaZero or their chess bot. So they beat
Lisa Doll.
Really, yes. And you might think, well, why is Google DeepMind playing all these like random games? What use is that? Well,
this is their origin story, wasn't it, with these games? Yeah.
Yeah, exactly. And these AI algorithms were able to defeat all humans at these games. And one of the founders, demystify, always thought throughout this endeavor to win at chess and things that if you could gamify biology, you could train an AI in the same way to become better than any human at that biological game, which in this case was protein folding.
But he was biased towards gamifying problems though, wasn't he? Because he himself, Demis, as a child, was he was an under-18s world champion in chess at one point in his life. So he definitely thought of things, I think, from a game perspective. But sure enough, it worked, didn't it? Yeah,
he was a genius. Yeah, I mean, in 2018, Google actually built off Fold It and the idea that clearly there is a pattern, if even a human can find this pattern. So there must be something there. So they trained an AI algorithm. So this led to AlphaFold, which we will discuss exactly how it works in a moment. So Google DeepMind scaled up this idea that there is an underlying pattern to find, and they trained AlphaFold on basically all the known protein structures at the time and trying to get this pattern out. And lo and behold, for CASP13, which was in 2018.
Yeah, confusing that, isn't it?
That was a bit confusing. They got the best score. They massively boost the score from around 40 to just under 60. So that's already up 50% increase in the accuracy.
Yeah, they were seeing stagnation in the scores, I believe. There was an increase in the early days, and then it was definitely plateauing, and then DeepMind came on the scene, and boom.
Boom, indeed. And then only in 2020, so 2 years later, with AlphaFold 2, they managed to get just under 90. So this just shows that scaling up the compute using these AI methods was really beneficial.
Yeah, and they quote unquote solved it by that point then, because it was at this score, this threshold for these predictions being useful and near enough to experimental structures.
Yeah, and this just created a huge shock to basically the whole world, because we're seeing headlines that AI systems have solved biology. So
we wanted to ask Jennifer, so firsthand, someone who had built this enormous skill set throughout their research career for determining these 3D structures experimentally, how did that feel to her now that a machine learning model was able to do it in a matter of minutes? So here's Jennifer to shed some light on that.
So at the beginning, you always have that kind of skepticism. Oh, they haven't really done it, because there's been this comparative modeling for years. This has been going on for a long time. The CASP competition that they won has been going for a long time, and every year there's something new, better comes out. So at the beginning, there's that kind of denial phase. Then I was like, oh, actually, this is quite good, because the first thing I did was actually check all of the structures that I had on disk that hadn't been released with the AlphaFold structures and see whether they matched up or not. Then you see that there are some that are really good, and with the confidence predictors, etc., this lets you know which ones are going to be worthwhile. But actually, I was quite excited because I've always thought of myself as a structural bioinformatician. So, and where the information that's interesting to me is when you have the structure. The getting the structure is nice, and I spent a lot of time doing it. But for me, the big thing that I'm interested in is the biological question and answering the biological question. And if there's a way to get there faster or easier, then that's sort of interest to me, because that allows me to get to where I want to be. And I think with anything, you have these new technologies, it's just the questions are still there. And if you answer one question, there's more questions. There's infinite amount of questions in the universe of things that we want to know and things that we want to do. So I was actually very excited about it all. But I love new tech developments. So I always think of everything as just a tool, and you're just trying to use everything at your disposal to get to the questions to help people in the end as the end goal, I think.
Well, I really like Jennifer's response to that, because just highlighting that the core goal is actually to understand biology.
Yeah.
And of course, it makes sense that the initial reaction to such a thing would be a bit of denial. It's like, oh my days, there's no way it can do this.
Yes.
But nonetheless, if it leads to understanding biology better, then it's a great thing. So I love that from Jennifer.
Yeah, no, it's so nice, wasn't it? And to give some scale as to how much speed up we saw here. So there were 150,000 structures determined over 6 decades to get the training data for AlphaFold, and that was thousands and thousands of biologists that put so much time and money into determining those structures. And then AlphaFold, as this prediction tool, was able to predict the structures of over 200 million proteins, which were determined by a relatively small team of just around 15 people in a few years. And this is kind of why people have described it as a significant step function in our understanding of proteins and therefore understanding of life, and had such wide-ranging applications, all the way from kind of malaria vaccines, now seeing different and new cancer treatments, enzyme design. So these are all the things we're going to kind of convey in the second half of the podcast. But really quickly, before we do that, we're going to give you a little bit of an intuition now, some nice demystification of what AlphaFold is actually doing and why it was able to absolutely smash the other computational tools, and some inspiration that maybe chatbots have even drawn from it in today's world. So shall we get into it?
Let's do it.
Okay, so Riku, do you want to tell us a little bit about what is going under the hood and why AlphaFold was able to crack this problem?
It's a meaty task to explain this one. So I'm going to speak mostly about AlphaFold 2, but just like AlphaFold 1, it was trained on the protein databank, which had basically all the known experimentally tested protein structures.
Yeah, which is what Jennifer now oversees as well as part of her job.
Yes.
Just sorry to quickly chime in before you get started. Just to quickly, people might be asking why we're not talking about AlphaFold 1. The main reason for that, I believe, is just that AlphaFold 1, they kind of just took a very kind of off-the-shelf existing AI well, architecture is the technical way we describe it, but like the engine was one that had already been built for a different problem, which was actually for solving image classification tasks, a convolutional neural network. And they just kind of took that and shoved it into this problem, and it did all right. It was still kind of a small improvement on what we had previously, but it was really when they designed this new engine from scratch for the specific problem of protein folding, which led to AlphaFold 2.
Yes,
Sorry.
and we call that an end-to-end system. So, they designed it from scratch to handle straight from the amino acid sequence.
Yep.
So like the raw letters of life, if I want to be all poetical about it. And then it directly predicts the 3D structure. So there's kind of no weaving together separate steps. It's all end-to-end. And you can imagine that gives the model absolute flexibility to kind of learn any possible pattern, rather than imagine if you train separate things, you weave them together. There might be some like long range kind of patterns that will be missed in that approach. So
makes sense.
Hopefully that makes sense why I use end-to-end system. And the core components to AlphaFold 2 was the enormous kind of release of compute power that was the world kind of witnessed after GPUs and things and deep learning all became much more accessible from like a hardware perspective. And of course, Google had a lot of compute power, but also, quote unquote, much, much better machine learning.
Okay.
And the core infrastructure here was this thing called the Evo former and attention mechanisms. So I won't go into that too much, but I mean, the attention mechanism is the same kind of technology that comes under ChatGPT and these large language models. And you can just think of it as a way that allows these models to kind of focus on different parts of the input. So in this case, it can look at exactly how different parts of the amino acid sequence relate to each other.
Yeah.
What was really cool though about the architecture of AlphaFold 2 was that it had this bidirectionality. So what that really means is you imagine you can have this sequence of amino acids, and you have this, they call it the evolutionary correlation. So you can think of there's these amino acid sequences, and you can see that there's some correlation. So maybe they react in similar ways a lot. So in that sense, you could kind of intuit that they're close together in this 3D space, but you don't really know.
Right. So this is the multiple sequence alignment, is it? I believe the MSA, I think.
Yeah.
So yeah, I believe this is where, rather than just looking at a single amino acid sequence on its own, the intuition there is it's useful to look at how similar amino acid sequence look across different living organisms and how they kind of change through evolution. So you can understand that if us as humans and then a mouse or a rat have similar proteins that are kind of slightly different, it's useful to look at the segments of that sequence which actually remain the same across those different organisms, and therefore those proteins have the same function. The intuition is there is we think that those bits would be quite important in predicting the structure.
Right, yeah, and maybe even close together, right, in the structural space.
Exactly.
So that's one thing, but it's of course not that simple because it's this big cotton wool mess. Yeah. So just because you're close together, it doesn't mean you're connected, right? So
true.
That's where you need this pair view. So this is much more like a geometric. You can think of like a jigsaw here.
Okay.
But maybe like a weird one where it's not like a grid, but where yes, two things might be close together, but they might not have that kind of key and hole kind of well-fitting alignment. So this is about the physical fit, like what is actually physically possible.
Okay.
So the Evo former was this mechanism that had this bidirectionality where it would solve this problem through understanding the MSA view and this paired physical view.
And I think to use your explanation of this being this kind of end-to-end system, that I think the key breakthrough was that previously models which looked at these two different aspects of the protein data, they would do it in kind of isolation, whereas this Evo former that Riku was just describing allowed that information with this bidirectionality to kind of inform each other. So the evolutionary aspects of the sequence would inform the structure, and the structure would inform the aspect of the model that's looking at the evolution, and vice versa. It was all kind of contained within this same system.
Nice, yeah. I mean, you can see how they'd be related, and allowing it to go between the two is really important.
Yeah.
The last part of the training of AlphaFold 2, which I thought was really cool, I didn't know about, was this thing called self-distillation. And really simply, this is basically where the protein database is big, but when it comes to trying to train an AI system to solve life, you can imagine that it might not be big enough. So What they did was they of course trained it on the data set that they had experimentally validated.
150,000, yeah.
Yep. And then there's also much more data where you can imagine there are lots of sequences, but we haven't got the structure yet. Self-distillation is where you give your model that's been trained on the good data to predict the structures, and using the confidence score of the model, so the model can say, I'm not sure if this is a structure, like this cotton wool looks pretty bad. Or it goes, this cotton wool looks exactly like how it should, in my knowledge. So you trust the model's confidence score, and you go, right, if it's really confident, we're going to make that into one of the training instances. So you do that, and they found, again, massive performance increase.
And then you retrain it with that new data, right?
Exactly, yeah. It shows that the patterns found in the original data set do generalize. And if you take those generalizations as ground truth, you can kind of keep learning.
Okay. Right, so is that kind of like if you've read a textbook on a certain topic really, really well, and you understand that exactly, that you then feel confident enough to write yourself some like new questions for the test, which are like variations of the questions which might be in the textbook, for example, and then before the test, you test yourself on everything?
I think that's a good one. Another analogy we could think of as well is if you think of these large language models, they're trained on so much data, so much text. Some of it's really good, some of it's really shit. And now people are looking to use the high quality outputs of language models, which is, I think, obviously a lot better than a lot of the Reddit posts I read. And you can see how using that in addition to what's being used could be better as well.
Which is in that world, which it's the same sort of thing, but synthetic data is what people have been calling it in the language world, isn't it? Which we've spoken previously about how it feels really murky and wrong, doesn't it? But
it worked for AlphaFold, right?
It clearly worked, yeah. Yeah, and just a couple of other really kind of quirky and non-intuitive things that they did to really improve the predictions of AlphaFold, which, as we now know, it worked. So as kind of strange as they feel, maybe we can take inspiration in other areas of machine learning. But the first of which was that, similar to this self-distillation thing, they also used this process called recycling, which is basically if you take the amino acid sequence, it makes its prediction of the 3D structure. You don't just take that structure and then use it in its final form. What they did was they took that predicted structure and then they actually fed it back through the model with the original sequence and said, okay, this is what you guessed first time, now give it another go. And they do that multiple times. And as strange as it seems, that actually results in it getting better and better. And they do it kind of multiple times. And this process of recycling results in a more accurate structure prediction.
Wow,
so,
I did not know that.
Very similar to the self-distillation, but it's basically saying, we don't trust your first guess. But now that you've seen a rough structure, try and give it another go. So that was the first sort of maybe non-intuitive one. The second of which I think scares some biologists quite a bit, is that they actually didn't force AlphaFold to maintain probably the most important assumption of any protein, which is that the amino acid sequence is a sort of singular chain, that everything is connected in a row. They didn't force it to make it a chain. So AlphaFold actually learned to eventually predict the structure in a chain format. But along the way of making that prediction, going from an amino acid sequence, AlphaFold actually is allowed to break that chain, and segments of the sequence are allowed to move and twist in isolation and then kind of rejoin at the end. So this is something that's really counterintuitive, but it results in better performance. And I think the reason I wanted to mention that is just because it's a really nice example of where we have this big disjoint between what machine learning models can do and like physical reality, and that actually results in these models performing better. So, when we let them do something which we know isn't going on in the real world, they perform better. So it shows that they learn this kind of much more complex stuff and these complex patterns than are even possible in the real world. But it results in them doing the task that we asked them to do with better performance. So, yeah, it's a very strange one, but it's one where I think people keep a close eye, because it's often where you get these kind of discrepancies that concern some people.
Wow. And it didn't just stop there. So when I heard about AlphaFold 3, I thought it was just like a better version of AlphaFold 2. But it actually turns out that whilst AlphaFold 2 solves the protein folding problem, AlphaFold 3 extended this to predict the structure of all kinds of things. So now we're talking about RNA, DNA, ligands, and chemical modifications. I don't really know what the last two are. I don't know if you can shed some light on the non-bio people out here.
Yeah, well, I think when we talked before about how we've got structures through all different scales of life, and then we have interactions too. This is a big thing, that a lot of the reason we want to know a structure is because we want to know what it's going to bind to and how it will interact with other molecules. These are all the questions that AlphaFold 3 was looking to answer as well. So it can generate these joint 3D structures, which this gives us a really comprehensive understanding of the biological world, because things don't work and operate in isolation. They're constantly interacting and reacting with other things.
Like your lactose intolerance.
Like your lactose
you need
intolerance.
Your lactase and your lactose.
There you go.
Right.
Yeah.
All right. Okay, I'm getting it.
You're getting it. So yes, whilst on its own it was also an improvement in protein structure prediction, we've got all these new biological questions that it was able to answer. In terms of these interaction predictions, it's at least a 50% improvement from these previous models. So that was, again, really improving what biologists can know and understanding about life, and then go and test those things in the lab. There are a lot of kind of similarities with AlphaFold 2 and AlphaFold 3 in terms of what it's doing under the hood. So we're not going to go into it as a kind of whole separate thing, but just one really interesting point I think to note, which was a huge new improvement, which again, very similar to other things we're seeing in the AI space today, is that AlphaFold 3 contained this new element which was called the diffusion network. And you may have come across this term diffusion before, especially if you listen to some of our episodes, but this is the technique that is used in modern image generation. So going from kind of randomness, and then you ask it to do something, and then it slowly, like tuning static on a TV, comes out with this kind of beautiful image that you've asked it for. They do a very similar thing with AlphaFold 3, where we start with this cloud of the atoms which make up the molecule that we're looking at, and then through this training process, this kind of random noisy cloud of atoms slowly forms this structure of this protein or this DNA or RNA that we're interested in, that has the structure that we're looking for from the sequence that we've given it. And yeah, with these two new tools now, we've been able to answer all these new biological questions, and we're seeing incredible research innovation that's just been hugely accelerated, probably at a rate we've never seen before in the scientific community, from a singular computational tool that's come out. And we're going to get into all of those in the second half. But yeah, I think we're definitely in need of a fun fact break, aren't we, Riku? It's a lot of stuff we've covered there.
I am.
Okay, should we do it?
Let's do it.
Okay. You go first.
Am I going first? Oh my days. Right.
I can go first. Shall I go first?
You go first.
Okay. That means you're not prepared. You're going to read whilst I'm telling you my fun
No,
facts.
I'm listening.
Okay. Okay. No biology at all in this. Completely unrelated. Just a random fun fact. But last month, an Airbnb host in New York submitted a bunch of images to the Airbnb's complaints team, showing significant damage that was done to their rental property. And the pictures showed a coffee table with this massive crack down the middle, staining all on the mattress, damage to a robot vacuum cleaner, a sofa was damaged, microwave, TV, air conditioner. So much stuff had been damaged in this property and was shown in these photos. And the guest who had stayed in there was subsequently charged more than $12,000 in damages by Airbnb. But they were denying all of it. They said that they hadn't done anything to the apartment. They left it in perfect condition. And it later transpired that all of the images were AI generated. And in fact, no damage had been done at all to the property. And yeah, the guest eventually received an apology and a full refund for their stay, which actually amounted to $4,500. So they'd been there for a while, I think. But yeah, the article that I was reading on this actually mentioned that insurance companies have seen this huge spike in false claims since these generative AI tools have come out, to like vehicles and repairs in their home, all using AI generated images.
That's crazy.
I know. So not really a fun fact, it's actually kind of a bit of an annoying fact, but yeah.
That's frustrating.
Don't get any ideas, listeners.
Wow, sketchy. Be careful.
Yeah. Okay, your turn.
I'm glad you went first, because mine's a little bit biological.
Oh, really?
Very, very slightly, though.
Okay.
Doesn't really have an AI in it, to be honest with you.
Okay. We're getting to that point, are we?
No,
35 episodes in.
But it does have learning from data.
Okay.
So guess what? So there was actually a group that tried to see whether pigeons could learn to detect cancer from cancer scans. And
is that you're stretching a bit here, saying a pigeon's an AI?
Well, yeah,
a real AI, bro. AI.
Well, an avian intelligence, right?
Avian.
Avian, is that how you say it? Isn't that a bird?
Oh, I don't know.
Avian. Avian animal. It's an avian. Okay, so I'm going to go again. So a group from University of California and Iowa turned to pigeons to cancer detection.
This is your second pigeon fun fact, Riku.
I know it is, isn't it? I love a pigeon. So yes, they were training pigeons to detect cancer from these images, these mammograms, and individually they didn't do that well, but as a group they did actually do similarly to humans. So this does suggest that maybe there is
Slightly disconcerting.
Yeah, or maybe there are clear patterns and maybe the task's quite easy. But birds can do it.
Okay, yeah, that was definitely a fun fact. Maybe not so AI related. Also, like your first pigeon fun fact. So I think we need to steer clear of the bird facts now, Riku.
I'll
for a different show. Cool. All right, back to the episode.
Cool. So let's hear a bit more about what is AlphaFold doing today. What projects is it contributing to?
Yeah.
Bit more about the ethics, maybe?
Exactly, yeah. Just firstly, though, because we've obviously said that it's massively impacting science and the scientific community. But first, this very powerful, big AI tool had to be kind of disseminated out into the public and people had to be able to reap the rewards of these predictions, because AlphaFold on its own is this huge, very powerful AI tool, and you need a lot of computational resources to run the model yourself. So people kind of got together and they thought, okay, we've now got this model, Google's got all this compute power, so we're going to release all of its predictions that we can do without people having to run the model and make the predictions themselves. Very, very generous and useful. So this resulted in the AlphaFold Protein Structure Database, the AFDB. And yeah, it's this free resource, this online platform website you can go to, and scientists around the world can now access all of these structure predictions that AlphaFold has made for non-commercial research, so for using them in their labs and to help speed up what previously would have taken them a very long time to experimentally understand these structures. And just a really nice quote here that I think helps to emphasize the impact of this database and releasing all this information. So John Jumper, who was leading the team within DeepMind, who was developing AlphaFold, he said this really nice quote, which is that the moment that AlphaFold is live to the world, we, as in the developers of AlphaFold, will no longer be the most important people in AlphaFold's story. So that then shifts the emphasis to all the amazing things that people are going to do with AlphaFold, rather than just the breakthrough in solving the problem itself. And yeah, we mentioned earlier that Jennifer is the coordinator and overseer of this database, but here she is now to talk a little bit about what exactly the database is, how it came about, and what her job involves.
Okay, so the Protein Data Bank in Europe, the PDBe, this is part of something called the European Bioinformatics Institute, which is a bigger bioinformatics institute of EMBL that allows lots of different groups to work together on these bioinformatic databases. So you might have heard of Uniprots, where you get like the sequences and everything like that. So we're all in the same section. The Protein Data Bank itself, we are kind of in three parts. We have data in, where we're taking the experimental structures. So it's on this data that AlphaFold was trained. And then we have a second part where we're bringing in more bioinformatics tools, information, etc., annotations. These are things to say about the proteins that we have of the experimental type in something called the Protein Data Bank Knowledge Base. And then the third part we have is the AlphaFold database. So this is the predicted AlphaFold structures. And we're all in the same team of the Protein Data Bank in Europe. And this means that there's a real interplay now between the experimental and the predicted structures, and what we can know about one from the other, which is really nice. I think it's really nice that it's all in one place, and then we can have this kind of you work out one thing for the experimental structures, perhaps you can apply it to the predicted structures or vice versa. It all supports everything else. What my role is for it is that I'm actually the coordinator of that. So it's like trying to get all these projects and the connectivity of everything together is very important to me. And bringing in all the people who have bioinformatic tools and all that kind of thing.
So just to talk a bit about the growth of this AlphaFold Protein Structure Database. So as of July 2021, when the paper came out, the number of predicted structures were 365,000.
Okay, so still sort of, over double the number of actual structure predictions that it was trained on.
Yeah, but this grew very quickly.
Okay.
So just by December that same year, it over doubled to 800,000.
Wow.
And then in the next month, so just January 2022, we got just under 1 million.
Wow.
But then within, about 6 months, in July in 2022, we end up with 214 million. So you can just imagine the impact this has and how it relates so much to John Jumper's quote. I mean, yes, AlphaFold was this magical engine that solved this crazy problem, but really it's how you use these protein structures and what all the researchers are doing these predictions that's going to have the huge impact.
Wow.
And I suppose this is what people mean by democratizing access to amazing technology like this.
Yep.
So in the first year that this database was released, it was accessed by over 500,000 users.
Wow.
And then by 2023, it had over 2 million users in over 190 countries. So it just shows that open sourcing these predictions was super useful and saved so much repetitive work.
Yeah.
Where if they closed sourced it, imagine how many of the same protein was painstakingly structured.
True.
But they released it, so it only had to be structured once. So.
Yeah, but crucially, obviously, we have to remember that these were just the predictions from the model, and researchers and experimentalists still had to go and check that structure was exactly as the model had predicted it, or close enough, as we said, with that kind of CASP score, the global distance test between 0 and 100. We want to make sure that all of those are sort of above 90, and we can only do that when we experimentally validate it. But having the prediction in the first place really speeds up the kind of early exploration phases, and it just helps speed up that workflow so much. So yeah, as Riku said, a lot less time spent on those painstakingly slow steps of getting to that biological question that, as Jennifer nicely put, is the actual thing we want answering. So yeah, here's Jennifer now to help explain how these experimentally determined structures and how the predictions are all kind of linked together. And it was this kind of natural relationship that formed between the institutions which were already managing these databases of the actual experimental data and DeepMind, who were making all these new predictions, over 200 million. There was obviously this natural relationship which was formed here, and these data sets kind of merge. And this has largely been Jennifer's job. So here she is to explain that.
I think there was a recognition that, the reason that this was able to be done was because you have this old, the PDBe is 50 odd years old. It's been going for a long time, very well curated, very well labeled data, etc. That's in very high quality. And they managed to train it on actually for a training data set for an AI kind of thing. This is actually quite small, but because it was so rich, this allowed this to happen. So I think it was nice that GDM, Google DeepMind, and EBI could work together on this. And then I think there also this appreciation that, yes, you have all these structures, but you need to get them to the right audience, and the audience that could benefit from it understand them. And then a big part of the EBI is training people to use our resources. And so we have a lot of training to do with the AlphaFold database that helps people who maybe not have a computational biology background understand and use these data. And I think that's what a really big strength of our partnership is that we can allow for that. Right.
Yeah, it's very interesting that, they kind of provided all that. It was all kind of open source as well, but it's very nice that has then kind of come back around almost, and it's feeding back into kind of what birthed it in the first place almost. So just curious, you obviously touched on the fact that you have these different kind of databases now, some obviously linking to AlphaFold and the machine learning predictions, others linking to experimentally determined structures. I believe, if I understand correctly, from kind of your tenure with the database, you've helped implement lots of features which really help people to kind of look across those databases. I'm just curious how they link up. Are the predictions, are they in a similar format to what you'd kind of determine experimentally, or what's the link there?
Okay, so when you deposit something to the PDBe, you have something called the coordinates. That's the position of the atoms in space of how this thing looks in 3D. And that is essentially the same whether it's an experiment or a prediction. Then what's different is the experimental has the experimental data that goes with that. So in crystallography, this would be electron density. You have the volumes when it's electron microscopy that that model has been fitted into. You don't have that with the predicted ones. You have other things. You have confidence metrics instead to look at to say how confident that prediction is. So the format is very similar, and essentially the basics of it is the same. We have something called, I don't want to bore you with the details, but we have something called a MMSIF format that's the same between the two, or a PDB format, which is a more basic version. It's the metadata that's different between them. There's small differences between the files. But this allows you, and then to go between them, we collaborate a lot with Martin Steinegger. He does fold seek that allows you to look at a fold and then see how it goes between. You can use that search against experimental or the predicted. It doesn't really matter. It's the same technology that allows you to move between the spaces, which is where it's very interesting, because you have maybe a lot of the time, in order to get something to crystallize or to get an experimental structure, you have to take a chunk of the protein. You don't always get the full length. If you predicted a sequence, you have the full length, but it might not all be as high confidence. And then you can compare the two, or you might not know anything about the predicted one. You can get the experimental one's got a ligand, it's got more known about it, this, that, and the other. And you can, or say you know a lot about something in mouse, but you're looking at, I don't know, some sort of rat or something, but you could infer across, which is, I think, is where the real power comes from. It's data aggregation that gives you the power.
That's so fascinating to hear from Jennifer. And I always wondered when I first saw about AlphaFold, when they say solved protein folding, was it actually, how do you know the predictions are true? And I guess that really nicely explains that they're just predictions.
Yes.
So I think it's really important that they've grounded this relationship between the predictions and what's actually been experimentally verified.
Yeah.
And from all the news articles and experimental results, clearly there's a really strong alignment between results. But I think this really paves into the philosophy of making sure these predictions are open sourced when it comes to validating the results. So Jennifer also speaks a bit more on this.
As part of the EBI, so we do open source data. I mean, it's the same with the PDB that allowed all this to be generated. And we have this kind of reliable funding, because we're not a research lab, we're infrastructure, we're a facility that provides a service. So yeah, this is a commitment that EMBL has, is to have this open science, to have these databases, to have these resources that everyone can access, and to access open source with any kind of no restrictions, like people. Same with all of the programs that we generate and pipelines that we make to look at the data is the same. Make everything open source and then see what people manage to do with it. Because I think that's also a big appeal of why people want to work for the EBI, why I wanted to work for this, is that it's contributing to this bigger goal of all human knowledge. It shouldn't belong to one person, it should be to everyone. So we have a strong commitment to that. It's a CCP by 4.0 license that we have for everything. I mean, it's the same for our knowledge base, graph database, etc. I know that pharmaceutical companies download it and they do what they do with it. I don't know what they do, but they like it, they take it, and they get use out of it, which is amazing. Because sometimes, even commercial entities, they need to obviously keep things secret so that they can get their patents and everything, and that's fine. But we should be giving this information out to people, and eventually we get the data back in the end. So.
Wow. Yeah, I think I said this to Jennifer as well there, but just really set the kind of precedent within the biological community, and I think the sort of machine learning community more broadly there, for, initially just making everything open, which is, as we know, helped people massively and democratize that access. But just one really important point to note actually was there was a tiny bit of controversy when they released AlphaFold 3, because it wasn't initially released as open as the AlphaFold 2 model was. We've done a little short stuff episode recently, haven't we, Riku, just about what kind of open sourcing is in the machine learning community and the different levels of how open these companies are with their code and their models. But initially with AlphaFold 3, they didn't actually release the code which showed how this model worked and what exactly it was doing, even though it had been kind of published in scientific journals about the kind of breakthroughs. And within hours of that publication of the actual kind of research article, over 1,000 scientists actually signed a letter sort of criticizing this decision not to release the code along with the research paper. But DeepMind then did sort of later respond later that year in 2024 by releasing the model code and the sort of parameters, so the brain that is used in AlphaFold, to different academic groups for them to actually see what was going on under the hood, which is why we were obviously able to talk about it earlier on in this episode. But crucially as well, though, with AlphaFold 3, they've actually restricted the access to these predictions so that so that they're only available for non-commercial use, whereas with AlphaFold 2, you could do absolutely whatever you wanted with those predictions, whereas now it's kind of mainly being used within a research setting, and it's sort of prohibiting uses for commercial activities or to train other sort of machine learning models as well.
I think this decision to not fully open source AlphaFold 3 is really alluding to problems that we've seen and been speaking about in AI for a long time. So it's not specific to AlphaFold. And it's largely about this idea of, just to quote Spider-Man, but, with great power comes great responsibility. And as the developers of such a tool, you do have to make a decision, if I release this to the world, what is the expected benefit and what is the possible harm? And yes, with this tool, we can understand biology, and with AlphaFold 3, it's not just proteins, but it's all kinds of molecules. You can see that this is going to massively contribute to medicine, people's longevity, their health, and impact people's lives massively. But, I mean, on the doom and gloom side of things, you can imagine that you can just make a whole new, dare I say, coronavirus and stop the world. So
a whole range of bioweapons, potentially.
Yeah, so I guess that is their motivation. They're thinking, you know what, we don't want a corona times 1,000. And the other side of it as well is open science and controllability. So yes, if you open source it and release it, it does allow other people to innovate on top of your work, which can be great. But also, given the high sensitivity, the importance of these predictions, you might want to control access to this model, because you might, if you tamper with the predictions and you open source them and someone else builds off that and they're all wrong, you could also see a huge ethical problem there. So it does sound like they stayed on the side of safety, which, I can definitely understand their decision there.
Yeah, I think it was right to initially be cautious with, like you said as well, the power that's now come from these new predictions.
Yeah, and these systems are also really big, so they have this controlled API, so you can ask for permission to use the model, maybe give it a sequence and it will give you the structure.
Yeah. A
bit like how you use ChatGPT, it's not running on your machine, it's running on someone else's machine. And you could also imagine that if they think you're doing some slightly sketchy protein folding, they could just deny you access to the API, and that just means that you can no longer use the model online.
Right.
Which does sound great, but also you can imagine that this is a completely centralized system of control, and that's another one of the trade-offs, right? So
yeah. I think, though, obviously, we've never had tools this powerful before in predicting these kind of amazing biological questions. So I think we're still very much feeling out this space and understanding where to regulate, what to kind of gatekeep. And it seems as though the default is to be very open with all these predictions, but I think rightly so, they're being very cautious here. But just to note, though, I think there's a lot of scaremongering and press around all of the dangerous aspects that tools like AlphaFold now unlock, and these kind of biosecurity questions. However, most experts in the field actually describe things like AlphaFold as a kind of force multiplier, meaning that they sort of increase what we can already do and speed it up, as we were discussing before, but maybe don't uncover a whole new class of new molecules or bioweapons that we didn't have before. So it's changing the landscape slightly, but the good thing within the scientific community and experimental biology is that we have these very robust and tested safety frameworks which are already in place to make sure that we don't accidentally create something really harmful or pathogenic or contagious. Just because we now have these new tools which speed up some of those steps and that kind of research doesn't necessarily mean those frameworks can't contain certain harmful things.
Cool. I think that does cover the ethical landscape. So how about we talk about some more positive looking forwards?
Let's do it. Okay, so we've talked about what AlphaFold is, how it works, how people are getting its predictions, but what is it doing? How is it actually impacting science and us and the world that we live in? So I think one of the main ones which we see talked about a lot in the news and people may be aware of from the kind of most intuitive things that we can do with AlphaFold is in drug discovery and pharmaceuticals. So the primary focus is basically to be able to develop new therapeutics and proteins as part of those drugs and compounds that have these functions that we know we want in proteins and in drugs and therapeutics to cure different kinds of illnesses and fight different molecules like cancers. And we want to know things about the structure of these molecules. We want to design new structures as well. So drug design is this really kind of intuitive one that it's massively helping to accelerate research in this space. And I think, again, the most intuitive way to understand this is that, determining structures of proteins and different molecules within drug compounds was previously a very time-consuming and costly step within that drug discovery pipeline. And if we can just very accurately predict the structure of those proteins or even kind of generate a new one, you can imagine how quickly that would speed things up, going from potentially months, years, as Jennifer was saying earlier, to potentially seconds, which is an order of magnitude change that I don't think many people can comprehend or many industries have ever experienced before. But it could potentially and likely reduce the cost of developing a new drug from, I think, the current average of around $3 billion US. So this is actually what spurred on Demis, who was CEO of DeepMind and pivotal in creating AlphaFold, as we talked about earlier. Sir Demis now, actually, sorry. Is the founder and CEO of this new startup called Isomorphic Labs, which is an Alphabet, so Google parent company startup, which is specifically focusing on using tools like AlphaFold and developing new tools to completely flip the drug design and pharmaceutical industry on its head and have this aim to cure lots and lots of currently uncured diseases and help save lots and lots of lives. And this also gets in this kind of world of personalized medicine as well, that, we no longer have a one drug fits all, but potentially if we have very quick pipelines for developing new drugs, we can have much more personalized medicine, which you have kind of fewer side effects to and is much more tailored to you as an individual and therefore more kind of effective.
And just as a practical example of this, we actually saw that AlphaFold was used to predict structures of several COVID proteins. So this was useful for vaccine development as a whole, enhancing preventative medicine and not just kind of curing things once you've got a disease after the fact.
Yeah, exactly.
We're also seeing you can design enzymes to fix all sorts of problems with the climate. So you can imagine biorenewable materials. So designing molecules that break down plastic. You can create more healthy, more resilient crops.
Yeah, so this is getting into this kind of generative aspect now. So we obviously have predicting protein structures from the sequence. But what this has started to unlock is this whole realm of now developing new proteins with these functions that we want. So when we said that AlphaFold and John Jumper and Demis won the Nobel Prize for this in 2024, they actually only won half the Nobel Prize for in chemistry that year, because the other half went to David Baker, who we spoke about earlier, for developing Rosetta, this early predictive model, and folded the game. But the Nobel Prize wasn't for that. It was actually for this tool that he developed called RF diffusion, which, as we were talking about, we had this kind of image generator model, but for proteins. He was the first to kind of develop this idea and was able to develop new proteins with these functions that we wanted. And their lab actually had this incredible research where they were able to develop anti-venom for snake bites without actually having to kind of milk the snake itself and actually get some of the venom to produce the anti-venom, which sometimes people react quite badly to. And they were able to generate new proteins which were able to fight that venom. So that just sort of gives you an idea as to all the different things that you could do if you could generate these new structures that do exactly what you want them to do with drug design and fighting climate change and ecology, all these things which are now being unlocked by AlphaFold and all the things that have come about because of it.
Yeah, you can see how useful it will be to have one kind of AI system that will generate sequencing of the amino acids, and the other one, the structure, one that can infer the properties, and now you have this kind of end-to-end system that you can just produce almost any molecule,
right? You can kind of reverse engineer it, exactly.
But there is a really big elephant standing in the room right now, and that is that these are all predictions and not truths. So we do need to continue experimental validation. We need to know that just like with ChatGPT and these other AI systems, they're trained on their training data.
Yep.
We don't know how well they will perform on very different types of data
New
structures.
tasks,
Yeah, we still need people to be validating this and looking for those regions where maybe these models are not so accurate. And what better person to ask for their opinion than Jennifer, who in their very recent paper talks a lot about the different confidence metrics that come out of using AlphaFold models.
Wow.
Okay, so I think the PLDDT, the predicted local confidence, is the easiest one. So we have this kind of color gradient, and it goes from 0 to 100, with 100 being very confident and 0 being, I have no idea. And it is colored. And the little thing we always say, if it's blue, it's probably true. It's kind of like the darker blue, 90 plus is very, I mean, those are the ones that when I looked at my structures that the training set that they hadn't seen, that they match very nicely, even the side chains, etc. But it gives you an idea of confidence. Like if it's high, then you know that's kind of like very confident, and if it's low, then it's probably a bit not sure about those positions of those atoms. And I think this is essential as well, because sometimes I've had people go, oh, AlphaFold got it wrong, it doesn't match this thing or whatever, and then you go look at the PLDDT, or they haven't reported it, or when you look at it, it's very, very low, and you're like, it says itself that it's not right. It's not wrong, it just says it's low. It doesn't have any confidence, it's just done something. And I think sometimes where the prediction hasn't worked can also be highly informative. And the question is, why did it not work? Why is it not confident? That is also telling you something there, telling you to go investigate something interesting there. Like often it's an area of disorder. Not all the time, but it can be an area of disorder. So there is no one confirmation that you'd expect that area to be in. So obviously it can't be confident that it has, when it gives you one model, is the right area. And then the other one that I think people find a bit harder but is very important, is the PAE. So this is how confident one area is in position to another area. So this is what gives you an idea of long range positional confidence, because you can have a very confident fold of one structural unit of a protein called a domain, and another one also very confident. It has good PLDDT, everything, the PAE within it is all very high. But then you've got to think, where is the position of these two things to each other? They both can be well predicted, but there could be some sort of link in between, and they can move around, and their positioning can be unknown, that where they should be from each other. And I think what I find really interesting about the PAE is that it's actually asymmetrical, because people think, oh, if this one's confident with this one, then this one should be equally confident in this. But it's not actually, it's asymmetrical. Often it looks symmetrical, but you've got to think, if you had one, say you were in your office there, and I'm on a bus or in a car or something, and you told me your location, I can be very confident in your location because you're staying in that one position. But if I was like driving around, you wouldn't be very confident exactly where my position could possibly be, or then my journey, and that's how the PA would report the same. I'd be like, okay, he's there. You'd be like, she's could be around here. But we're not quite sure. She's in the city, but we don't know exactly where she is. And I think that's also a very interesting one and an important one to say, oh, are these domains positioned accurately to each other?
Yeah, that's fascinating.
Yeah.
And maybe now a very naive question possibly from a computationalist, but to sort of extend your analogy then. So intuitively from how you just described that, I would imagine that the sort of PAE has much more significance in terms of the function of the protein than compared to maybe, let's say, where you are, which seat you are on the bus, for example, if I've kind of understood PLDDT correctly. So is there, is it very context specific? Which one is kind of has more of an impact as to the biological question you're answering, or are they equally as important, would you say?
I think you need to look at both, and also what is your biological question? Because if your biological question is how is this ligand binding, then your PLDDT is very essential, and actually where the other domains are compared to that one active site isn't interesting to you or important. The rest of the protein structure could be very badly predicted. But if the little bit that you're interested in is well predicted, then you're happy. Conversely, if you wanted to know, oh, is this regulatory domain, how would that be positioned with something else, and that was your question, then actually you could maybe get away with a lower PLDDT. You just want the general fold, but you want how things are positioned to each other. So I think you always have to look at these things quite holistically.
Yeah. if a lab is going and kind of utilizing one of those predictions, and then they go and validate it experimentally, and there's some form of kind of inconsistency, how sort of easy is that for them to detect, and how does that then, if at all, sort of feed back into the database or change the prediction, or what's that kind of feedback loop look like?
So at the moment there isn't one, but this is something we want to move towards, that there is a way of, because I always think a model is only as good as it is predictive. And you could have either, yes, you predict an interface or something and they do a mutation, does the break apart. It'd be really interesting to know which, and there's so many different experiments that could contribute to giving confidence and validation to these models, or not, or say that they're wrong, or also be used to create better models. So there's all these kind of, I don't know if you know about integrative hybrid structural biology, where you use things like, so I was talking about like the PA and things being positioned, but you can have labels that tell you the relative position of two things, RET, EPR, etc. That you could use that as a restraint, or you can use it as a validation of the models afterwards. And I think this is where things are really going to go now, is that, and also mutational data. It said that this was varied, you mutate it, does it fall apart, etc. I think there's so much opportunity there, and we really want to move into that direction. So we already have a little bit of that with this is why I mentioned the protein data bank knowledge base, because that's kind of, we have that as well, bringing in these extra, what we call annotations, this extra data of experiments. I think it's time to start doing the same for predicted things as well. Yeah. So watch this space, basically.
So moving on just to looking forwards in general, I think that when it comes to AI and sciences, the core word to think about is scale. And the size of these biological data sets are just way too big for any human to really understand in their tiny little biological brain. So we're seeing AI as becoming a fundamental tool in chemistry and biology. And we're going to see a world where you just wouldn't do these kinds of chemistry questions, biological questions without AI.
I think if we get these predictions right, and we now have these tools which can really answer these questions that before would have taken years to do so, I've heard it described before as solving what's known as a kind of root node problem, whereby in solving this one piece of the puzzle, rather than just going to kind of the next natural step along and you go to the next question, it actually unlocks this whole new tree of questions and possibilities that previously weren't possible. So it really is this step change where it's not just kind of another kind of biological question we've answered. It's unlocked this whole new field of research and accelerated things in a way that we've never seen before in this space. And yeah, people think it's really going to kind of revolutionize the world and the field of biology. I think Eric Schmidt, the former CEO of Google, and obviously has involvement with Google and DeepMind, said that he predicts that basically every kind of biologist and chemist moving forward at some point in their careers now will be able to kind of testament some of their work to AlphaFold and the work that it's done there.
So yeah, I think this is probably just a very small slice of the pie when it comes to all the different unimaginable ways this is going to contribute to science in the future. And I think as a result, a lot of people are awaiting AlphaFold 4, a bit like how we're always waiting for the next model. But I think it's good just to go back to John Jumper's quote about how it's actually other people that are actually going to be the main players when it comes to the impact of this technology, rather than those that developed it. And Jennifer actually had a really nice outlook on this, on how it's really the community effort that people are striving for, and how we actually need different specialists coming together to make the most of this technology. So let's listen to what Jennifer has to say.
For us, the major thing is going to be bringing in this kind of experimental information and bringing in more communities, linking to other resources, I think is very important. So you have all sorts of resources that have data that some of it would be better put in a kind of structural biology context, that if we can do that, we will. Looking at ways to compare the different structures with each other, technologies to look at that, a bit like fold SQL, that sort of thing. I think those kind of usability and ways to understand the data. For me, the big driving force is making the database as usable as possible. And to everything that we want to add, we also want to make sure it's like high quality and that it's very understandable to people. So really thinking about what we're adding and making sure that has a value add for the community before we do it. but at the same time bringing as much together as possible. That's the main aim of what we're going to go for, and involve as many people as possible as well, because community effort, I think accessibility is a big motivator for us, because so you want to get a good biological story, you need a clinician, and you need a tissue culture, you need your computational biologist, you're this, you're that, you're a biophysicist. So many people contribute to one thing now, and you can't expect all of them to be experts in everything. It's a bit mean, so you have to try and help people get the information that they need. Maybe they just need it for a very small punctual story. They don't want to go do a degree in bioinformatics just to do this one thing. They just want to get the information they have. And if we can do a lot of that, like you say, put the pipelines together so they don't have to go and do a command line interface analysis would be nice. But it's a lot of work. It's hard to do this, to kind of bring it into a way that everyone can understand. We actually have a UX UI designer on the team who works very hard trying to make it so that the data are in a way that everyone can find as well. Even just finding the data, you don't know what you don't know. I wonder if some of them have never been looked at. I'm not sure all of them have been accessed yet. But a big piece is this community engagement. That's what we want to get eventually. I always think, have you heard about the IKEA effect? You prefer things that you've been personally involved in creating. You make that table and it falls over, but you love it. So I think that's that's my philosophy with these things as well. One, we're a small team, get more people involved, and two, then I think people will value it more if everyone's involved.
Okay, so there you have it. And thank you so much to Jennifer for coming on and sharing her, what I imagine is very precious time with all this work and everything going on in this field of research right now. But yeah, we were very honoured to have her on to talk about how all of this new research is being facilitated with the AlphaFold database. And we're super excited to see what's to come, as I'm sure we're just at the tip of the iceberg with all this stuff. And it's a very prosperous and exciting time for science. So we hope we conveyed how impactful this breakthrough really was, and why we titled this episode AI's biggest breakthrough. And I think a lot of people now are starting to see the impacts it's having, and truly believe that it will touch kind of every human and impact their lives in the future. So yeah, we hope we conveyed that, and we hope you found it interesting, and we hope you can be a recipient of something that AlphaFold uncovers in the future. So yeah, thank you so much for listening.
Yeah, thank you so much. If you made it this far, I think this is going to be quite a long episode.
Yeah.
And yeah, please do, as always, get in touch if you have any questions or suggestions. Contact at artificiallyeverafter.com. You can also leave a comment on Spotify and maybe some other platforms.
And if you'd feel generous enough, feel free to support us on our Patreon, which you can get extra bonus episodes and content and behind the scenes bloopers. It helps us to support the podcast and keep it going, and keep it free without ads. So we'd love your support. But yeah, thank you so much for listening again, and we'll catch you next time.